now?
Yes, please.
Okay. And so to begin with, actually, okay, hello everyone, and thank you for coming to my presentation in our reading group on algorithmic execution while graph representation learning. And
Patricia, do you mind enlarge your presentation?
Oh yes, but it's because
At
okay,
least you can click the right arrow
yeah.
to kind of remove the right panel, right?
I can do that by showing in the full screen, but just like to begin with, to begin with, actually, earlier today, Emily told me about like is this somewhat related to the graph pointer neural networks, and I just took a quick glance at this paper, and I should say that no. Although like this one is called the graph pointer neural networks, and today there will include we will include two papers, and one of them is called pointer graph networks. And I'm pretty sure that they are not about the same thing. And the graph pointer neural network, that one, is basically about a new architecture of graph neural network. And the pointer graph neural networks and this tool works, we can, they are probably more on the application side of the graph neural networks. And those both works are for using graph neural networks to execute traditional algorithms. And some other references include the author's presentation. This is a live presentation. And also we can find some other related slides from the author's personal website. And special thanks to Zinyo, who recommended those papers to me when I found it hard to find an interesting topic to share with. And the motivation, as the author mentioned, is that, so let's say the traditional algorithms, for example, on graphs, they are different from the methodologies that we use on the neural networks. So typically the traditional algorithms, the inputs must match some specifications. And for the graph neural networks, we can operate some raw input of like a very not not really have a specific format. And the traditional algorithms are typically not so robust to task variations. But for the neural networks, the models are reusable for different tasks. And as for the interpretability, this time traditional algorithms win. And it's also could be easily generalized to, the knowledge to other to the same tasks. And it's and also it works on small data set. So basically the algorithm and the neural network, they are like one's pro is another's cons. And so a lot of people are thinking about combining them together some way, or like using one on the other. And there's also some observations on the classical algorithms. And for example, some of them share the same subroutines, like the shortest path computation via Bellman-Ford algorithm and the reachability computation via breadth-first search. Both of them enumerate set of edges adjacent to a particular node. And also, like, there are different kinds of algorithms. Sometimes one focus on the one node at a time, and sometimes operating on multiple nodes at a time. So the first case gives us the possibility of computing multiple algorithms at the same time. And the second one raises new challenges of like whether or not we can handle different types of algorithms at the same time. And so far, researchers have studied a lot on like using the ground truth algorithm solution, or like sometimes we just call it an algorithm, to drive learning. That is to apply the algorithm to the neural network size. The authors' works, they are using neural networks, typically graph neural networks, to execute classical algorithms. And to start with, they use algorithms on graphs. So we see two mentions of graphs here, and we'll talk about what kinds of graph they're using later on. And they name this process as Neurograph algorithm execution. Okay. So basically, Neurograph algorithm execution is the approach that learns several algorithms simultaneously, as we just mentioned before. This is because of the nature that some algorithms share the same subroutines, and also provide a supervision signal. And the signal is driven by prior knowledge on classical algorithms behaviors, and thus transfer knowledge between different algorithms and learn them effectively. And the first work is on neural execution of graph algorithms. This is the topic of that paper. And to start with, graph plays two roles in this work. One is that the graph serves as part of the problem provided because it's focusing on graph algorithms. And the second role is that it is the input to a GNN because we are using a graph neural networks to execute it. So the graph is defined this way, with a set of nodes, or we can call it vertices, and with a set of edges, or like in nature, edges are the node pairs. And the GNN we use to execute this graph algorithm receives a sequence of T graph structured inputs. And in each of those input, sorry, in each of those inputs, each node has feature, and each edge also have, this one should be IJ in E. I will correct it later. And each step, there will be a node level output, Y, which we call it Y. And the architecture of the graph execution framework basically consists of three components. It's following the encoder process decoder architecture. I also put a link down here. This is where they cite the encoder process decoder architecture on. So first, it consists on encoder network. This network is algorithm specific, which means that for each algorithm, we have an encoder network and a decoder network that is specific to this algorithm. But the processor network P in the middle, this one is shared among all algorithms. So in a way, this framework is typically multitask learning. They share the processor networks among all of them. And so the encoder network takes a node feature and the previous step, latent feature H, and outputs an encoded input. And the processor takes the encoded input Z and the edge features and to generate the current state like latent features. And the decoder takes in the Z and latent feature H to generate the node level outputs Y.
Patricia, what is the encoded input? No, latency. Is it more like a recurrent neural network where the processor output is somehow fed back into the encoder?
It is.
What does previous latent feature H mean?
It's because we are having a sequence of graph structured inputs. So every time it takes in the previous state and it considers the previous state and to predict the current state.
Oh, maybe I don't understand the sequence word then. What is sequence here?
This is a sequence of the graph structured inputs because traditionally the graph, the algorithms that we run on graph typically involves a lot of steps. And so those sequence are is the steps of that algorithms.
So each of these graph structured input are not independent separate graphs?
They are not independent, they are dependent. Like
so they are part of a large gigantic graph. How are they dependent?
They are dependent because like for example, one graph is the for example, if like if we consider the reachability problem, and like if we want to compute what are the reachable nodes on a graph, and and in the first step we only mark the adjacent nodes, the neighbor nodes of these nodes as reachable, and the second step we merge the two hop neighbors as reachable, and so this is this so-called sequence.
Oh, so we are somehow working with the same graph.
Yeah, on the same graph but with different state.
With different states.
Yeah.
Okay,
and so yeah.
Maybe things will be a little bit more clearer once I see some examples. Thank you.
Yeah, and so and so they also provide a visualization of this idea. And on the left side of this figure, it shows the algorithm's nature, like from X to some sort of knowledge that we want to extract from it, Y, and update it sequentially. And but on the right hand side, there's the Neurograph algorithm executors behavior, basically. So this visualization is more or less like saying that how we infer those knowledge from the traditional graph, and to try to compute the and try to embed the input and try to compute the hidden states, so that we can also predict the Ys for next stage.
Patricia, I think I still do not have the clear picture about the motivation of the paper, and also the paper has utilized some new terminology, for example, graph algorithm executor. Okay, and you somehow say that, okay, we wanted to look at the graph algorithm level, but I still do not really have a big picture of like what this paper is trying to do. Without that picture, I could not really understand, for example, why we are considering that the input is a sequence of graph data. Okay, so what does that mean? Can you give us a like concrete example to illustrate the purpose of this paper?
Concrete example. I'm thinking.
Zanil, do you want to do that? Because I guess the paper is recommended by you.
Yeah, but I think in the slides there is some experiment. Maybe Patricia can show some of the applications this paper tries to solve.
Yeah, I am on this page where I put up some algorithm examples here, like the breadth first search algorithm for reachability computation. And in this case, like the X starts with all 0 but only 1, which means that in the first step, we only know that the starting point is reachable. And then it's updated. It's updated through the edges. And once an edge is reached, then we say that, okay, so this this one is marked as 1 as well, and the others are still remain 0. And also if previously this node is already marked as reachable, then it could not become unreachable. So it's always kept to be 1. And so basically, XIT means that is I reachable from S in no larger than T hops. And this is I think I didn't put other details of those examples on the slides, but
So for now we are looking at 2 very specific graph problems. The first is like the reachability test, right? The second is like shortest path calculation. For each graph problem, we can find a kind of couple of algorithms that can give the solution, right? So for each algorithm, actually is a procedure. And in that procedure, it will assign some sort of values to each node. I believe that's the kind of the sequence of the graph that you talked about earlier. Yeah. Is that case?
Yes.
Okay. So then what does the whole paper try to do here? I think earlier you mentioned that somehow we wanted to imitate the graph algorithms for different problems. Then what would be the output of this whole paper? Like what kind of problem it tried to study, given what kind of input? I guess the input is like a bunch of graph algorithms, and they are, the algorithm and formalized in the format that will be taken by their algorithm. Then what will be the output of the paper?
And so by learning on by learning on the given supervised data set, and they are able to somewhat captures the they end up in having a graph neural network that could execute the traditional algorithm on graph.
Is that a traditional algorithm, those graph algorithm as input to train this graph neural network?
It's like they are making the graph neural network to do to do the same as in the traditional algorithms.
Yeah, if it's the same, right, so then it's not interesting because we can just utilize the graph algorithm to solve it. It must have some additional power.
And not exactly the same. So for example, they can run multiple algorithms at a time, and so that like traditional algorithms cannot handle this multiple tasks at the same time.
I was saying, okay, go ahead, John.
Let me try to mention my best interpretation of what this is trying to do. I don't know whether this is a correct interpretation, but this is just my best effort to understand it. So I think at the end of the day, the real problem, if we can find or train a neural network that, let's say we are given a problem, a graph problem. Let's say we want to find, given a particular node, we want to identify all reachable nodes, right? So that is the solution. We want to find that out. So that is one problem that you want to somehow train the neural network on. Or there might be another problem, like I want to find the shortest path from this particular node to every other node that exists in the graph. So that might be another problem that you have to solve. So as long as the neural network provides that output given any input, using whatever magical solutions that it can come up with, I'll be happy. I don't care about how they do it. What I care is, at the end of the day, is getting the correct solution from the neural network, right? So that is what you want. But it seems that training that final outcome only from the input and output mapping. So like then the training data might be, this is the input graph, and this is the source node, and these are the all reachable output, right? So that would be the training data. And if in case of the shortest path, the training data might be this graph, this input node, and these are the shortest distances from that node to all other nodes in the graph. So that might be the training data. So I suspect they might try it. They may not have tried to train some kind of neural network based on that input training data to see whether they can somehow train that neural network to somehow magically come up with that mapping from individual node and the graph data, somehow come up with the reachable nodes or the shortest path. The problem is that that is just such a magical map, a quantum jump from the input to the final output. It's unlikely, or it might be very difficult to train a neural network just purely based on the data. So it seems the idea that these authors might have is that, we don't really have to train just input and output. We can actually train them based on the sequence of kind of steps that some existing example solutions are going through. So what we are trying to do is that we are actually training on not just input and output pair, but the sequence of kind of intermediate states that the various algorithms are going through in order to arrive at the final results. So if we can somehow then create a neural network that actually tries to mimic individual steps that these algorithms are going through, then that is more likely to be easier to train because it has more kind of intermediate steps, and that eventually it will arrive at the final solution. So maybe what they are trying to do is somehow train a neural network that somehow imitate whatever the input training data. And I think what Patricia is saying is that that kind of training data can come from just a single algorithm, but it doesn't have to be, right? So these intermediate steps, we can combine the intermediate steps coming from, I don't know how many other, let's say sorting, right? Sorting, or maybe bubble sorting steps, and the quick sorting steps, and radical sorting steps. So we kind of generate all these sequences and then give that as the training data for our neural network. And the claim seems to be that somehow these algorithms are magically able to come up with the right way of solving it by generalizing them together, maybe. So that is my best effort interpretation. I don't know whether it's correct or not.
Yeah, I think that is the correct way of understanding this. Yeah. So this is indeed what they are doing. And well, I personally find it's like interesting because I've never thought of handling things like this, but Yeah.
Yeah, probably I can also provide another viewpoint. So I think most of, like John's explanation is very correct to interpret this paper. And also like since this is like the very first paper in this line of research, and one of the very interesting finding is that by learning such intermediate execution results from some classical problems, for example, some easy problems like reachability and some kind of sortings, and they can utilizing this intermediate structure results to help help some more complicated problems such as like shortest parts or even some NP hard problems. And they shows that this kind of information transfer can even improve some of the earlier IL based results. So probably this, if we follow this line of research, there could be some of the harder problems that we don't have such intermediate results. For example, some planning or like portfolio optimizations. And we can also utilizing some of these classical graph algorithms to initialize this graph neural network to capture such like algorithm execution capacities to improve such information transfer. Yeah, this is my understanding.
Yeah, thank you. So yeah, so then I fear what they try to do is like previously we just have the input and output pair, right? So then the signal, if you look at the granularity, it's just a two cores. So if we input the intermediate steps, although they are designed for other different purposes, but then different algorithms actually they share something in common. So hopefully that it will give the graph neural network a much bigger power, and also like more fine granularity guidance in the middle. But I still have, probably Patricia, later you're going to mention that. I still have the question like how to leverage this intermediate signal. That's the first question. And the second question, how we can really make it generalizable to a different task. Because I can somehow have the feeling that, oh, indeed, if we handle the intermediate signals correctly, then we can have a better estimation on those parameters. And the graph neural network is very powerful. But then how we can leverage that to handle some unknown problem, which is completely different graph, like as you mentioned, right? Could be completely new graph problem. How we can utilize that. So probably you're going to mention that. So, but yeah, I just wanted to say that I'm waiting for the answers to those two questions.
Okay. Thank you for the discussion, and thank you for Danielle's explanations. And yeah, so maybe we go through this part together, and maybe in somewhere in the middle we can figure out the answer. Yeah. Okay. So this figure here is more on it's more abstract visualization of this idea. It's just showing those components of a between an algorithm and the executor, and how they are actually getting involved. And this one, the second picture we put here is from figure 2 of the paper. This is from a concrete example of the Bellman-Ford algorithm. This the algorithm is on the left, and the step of a message passing neural network is on the right. And this is, we will mention that the message passing neural network is what is the type of graph neural networks they actually use in practice. And the supervision signals comes from the algorithm itself. And
Patricia, can you elaborate that part? How we can utilize this intermediate signal to supervise the message passing neural network? Can you elaborate more?
This is okay. So this is because we from the hidden state. So Okay, from the hidden state on the right, we will have the decoder to generate some sort of
Hello.
and so we actually compare the oh, my internet connection is unstable. Oh, anyway, so so from the ground truth algorithms output, like because we know what the actual output should be at this step, and then we also have a prediction from the neural network so that we can compare it, and this is where this supervision comes from, according to my understanding.
Okay, gotcha. Thank you.
Yeah. And something more on the encoder network FA. It basically takes in the node features of node I at step T and the previous latent feature of node I. And also, like, if it is the first step and we do not have a previous latent feature, then it is set to be all 0. The output is an encoded input of node I at step T.
Why does it have one layer of indirection between H and Z? Can we just do like from HI to HI or HT minus I to HT? Why do they have this one layer of indirection? I don't understand that very well.
I think there's no specific explanation on this decision in the paper, and
okay, that's fine if the paper doesn't explain.
But anyway, I mean X has to be involved here because this one is the encoded inputs, which means that at least we should take in the input. But the H, maybe they just want to encode it so that within the input it consists some previous stage information.
Yeah, so then can you just do like HIT instead of introducing Z, one more additional layer of complexity? Can we just do HI of T is equal to F sub A XIT and HIT minus 1? That previous state, hidden state, somehow influences the next hidden state as well.
Oh, it's a good question, but sorry, I think I do not know the exact answer.
Yeah, actually in the paper there is another formula try to define HIT. So they are not the same thing. So for this HIT, it is a function of the Z.
Yes, we will see that later. Yeah, so there comes the processor network P, which is a shared network among all the different all the different algorithms, because now we are considering multiple algorithms at the same time. And H actually uses like the all edges information and all the encoded inputs at time T, and it generates all the latent features at step T. So so the previous question for like the benefits of including the previous hidden state in this way is probably also involving that we have some knowledge from the shared network, have some knowledge from the other algorithms as well in encoding the encoding the input. This is to my best understanding right now. Okay. And P also, like because we know that the traditional algorithms involve some termination decision, and P is also responsible for handling this. And to handle the termination of the algorithm, they specify another termination network. But the termination network, again, it is algorithm specific. And the termination network we are having for the within the like processor network, it handles all the algorithms terminations by computing the probability of of termination via another neural network. And the output layer is a logistic sigmoid activation, and it takes in all the latent features for all the nodes at step T, and also their average. This is its input, and the output will become a probability of termination. And after that is set as threshold, for example, 0.5. And if the threshold says that let's terminate it, then the algorithm it's terminated.
What is TA here?
TA. This one is the termination network. This is a neural network.
They try to compare the average value to the set and then decide whether they should be terminated or not.
I think so. Yeah. Or no, not really compare it to. It's like this one is just a according to their according to the descriptions later. This one is just a linear layer of transformation.
So somehow I fear for some algorithm, right? So we wish it converges. But then in this case, the average is going to be close to each other, I guess.
Probably this is the reason why they consider average as part of the input as well. So should we move on to the next page? Sorry.
Yes, please.
Okay.
Thank you.
And for the decoder network, it's also very straightforward that we take in the encoded input and also take in the latent features of node I at step T, and we generate an algorithm specific output of node I at step T. And if the algorithm hasn't been terminated, then we can move on to the next step. And in many cases, why is actually what we learn from this step, and it could be at least partly reused in XIT+1, which is the next step node feature. Oh, and by the way, that is also the reason why I say that they are not independent inputs. And some high-level design decisions include that because they want all algorithms to be executed simultaneously, So the network P is shared, as we just mentioned. And also they want the majority of the computation source be placed on the processor network P. So they do not want those algorithm-dependent networks to be overly complex. And they are all made into simply linear projections. And some and also because most algorithms, most algorithms on graph requires making some discrete decisions over neighbors, like which edge to take for the next step of computation. So the message passing neural network, they claim it to be a very suitable choice, especially when we use a maximization aggregator. And so about the message passing neural network, they propose it by comparing it to GATs. Graph attention are also used as baseline models in their work. So in GAT, the W is a learnable projection matrix, and alpha is the attention mechanism producing a scalar coefficient. And in the message passing neural networks, as we list here, M and U are neural networks producing vector messages. And this big O plus is some way of aggregating any sort of aggregator. And in practice, they found that with element-wise aggregation operator, it performs the best. And finally, what they are using for the component of P is a message passing neural network. And some details also include that they insert a self edge to every node to make it to make you being aware of your own information. And the M and U's, once again, because they their design principle, I guess, is to get rid of some complex decisions influence. I mean, they want every component to be as simple as possible, so as to and make it work in all. So M and U are once again made just linear projections. And the aggregator, they tried multiple variants. And they also, later on, they compared to GAT baselines. And for the data sets, they generated those graphs with like 20, 50, and 100 nodes, and following different strategies, like 7 or 8 strategies they're following. And the work is also listed here. And it's not the focus of this work. And for each edge in those graphs, they are actually making the edge the edge feature just a real value weight drawn uniformly from this range. And the benefit of this decision, they claimed, is that because the edge has some randomly sampled weights, so some of the solutions becomes unique, and the downstream evaluation becomes easier. And the previous examples we mentioned, that the algorithms that can easily be paralleled, and both algorithms initialized by randomly select a source node, and and later on aggregating neighborhood information and require discrete decisions. And also something to note is that for the baselines, for example, the GAT, they also do some tricks to make it better fit into this problem setting. They make the coefficients as sharp as possible, which means that try to mimic the edge selection. And this was the page that we were just on when we are talking about some possible applications of this work. So the breadth first search for reachability and the Bellman-Ford algorithm for the shortest path, they are actually here in the comparing them together, we found that there are some sort of subroutines, but yeah. But for the breadth first search, because there's no additional information we need to compute, we only need to know the whether or not a node is reachable, and that's all. So we can directly use the reachability that we predict for this step to be the next step input. And for the Bellman-Ford, which we want to compute the shortest path, we will also need the information of where's the which one is the predecessor, so that we actually need to predict who is the predecessor, and also like what is the shortest path length. So here we have so here we have two components of Y, and part of it goes into the next steps input. Okay. And also and if we decompose the problem in this way, the example of the Primes algorithm for minimum spanning trees could also be decomposed into like what is the initial state and what is the next step to be, and then we it also involves selection of the nodes. And XIT represents the is I in the partial MST tree built from S after T steps. It remains this true or false questions answer. But once again, we need to keep track of the predecessor. So similar as before, Y consists of X, I, T, and the P. And they both fit into the same framework in general. And some of the results, like they actually in the paper, they have a lot of discussions on those experiments and on those results, which is very detailed and very informative. If you're interested, I recommend going through those discussions. But here, what I'm listing is the results, the most direct results involved in the algorithms that we mentioned before, and all those results are the test cases where the training is on the graph of 20 nodes only. So it shows that the network actually learns something, some more general knowledge that could be applied to larger graphs.
I have a question here. So when they show the performance, do they train on the algorithm and test on the same algorithm?
They wait here. They I think
For
they
example,
can-
reachability. Do they
yeah,
train on reachability and test on reachability?
they I think they claimed to be trained on multiple algorithms at the same time, but for the specific figure,
Yeah, in this paper, I think they will train and test on the same algorithm, but on different type of the graph.
yeah, but I mean, do they train on multiple algorithms at the same time? They also claim to do that.
Yeah, they also shows that by training on multiple algorithms, they can, this kind of like multitask could help the transfer learning on.
Sunil, I can't hear you.
Yeah, I mean, they indeed show that by training on multiple tasks, the performance can be enhanced. But regarding to Izhou's question, they indeed train and test on the same like algorithm. Yeah.
So those are probably single algorithm results.
Yeah, I think they have a table for single task and then a table for like transfer learning, like multitask, I think.
Okay.
I think if we're saying that we train on let's say 10 different algorithms and then test on same algorithm, I feel it makes sense. But if we train on one algorithm and test on the same algorithm, what's the benefit of doing so, right? Because for example, for the reachability, we know that for BFS, this algorithm already know that it can handle the same problem, and we don't even have to learn it. We can just run that algorithm, we could get the output. Then what's the benefit that we train a graph neural network mimicking what this algorithm is doing and then try to provide the result?
Yeah, I think the setup you mentioned is more realistic, and I think maybe it's like the next step of the problems we can try. For example, for a new task that is really hard and don't have too much label, we can try some few shot, like fine tuning over GNN initialized from multiple classical graph algorithms and see whether we can gain some improvement. But
Right.
for this paper, I think they just show that GN can do that, but they didn't claim that GN can replace
I see.
the classical graph algorithm. Like the claim is different. They are more like the experimental exploration, nor not like we want to have a very efficient algorithm to replace those discrete graph algorithms. Yeah.
Mm-hmm. Okay, great. And the second question is related to the discussion on like we can train in a multitask learning setting so that we can benefit from multiple algorithms. But then the question related to that setting is like, how about the initial features? Because according to Patricia, your earlier slides, right? So different algorithms, actually the features are quite different.
Yeah.
So this initial X, right? Or the feature actually, in the neural network, the initial feature has nothing to do with the initial feature in each of the algorithms independent. Are they the same thing or they are different things?
You mean for the different algorithms?
For the initial feature of the neural network, graph neural network, and the initial feature for some specific algorithm, are they the same thing or they are different? Because both of them use X notation.
According to my understanding, it should be different from algorithm to algorithm.
From algorithm to algorithm, they're different. Then what would be the initial feature for the graph neural network? Are they also different for different algorithms? And if this is the case, then how we can handle multiple?
Wait. Do you mean the graph neural network of of the part P.
Yeah, for example, for the formula, when we do graph neural network, we need to transform the initial raw feature X into the next layer's latent representation. So then my question is like, what would be that initial feature in the graph neural network? So for some specific algorithm, of course, that initial X is different, and they don't have latent feature. What they have is just the XT at a different step. Right. So then my question, like for different tasks, do I need to utilize different initial features for graph neural network?
The graph neural network only let's see. My understanding is that the graph neural network only lives within the process network P, which is shared among all the different algorithms. So essentially, they are using the same
node feature, which has nothing to do with the initial feature in those algorithms.
Yeah.
But can you go back to the couple of examples you're showing, the graph algorithm examples?
The examples. Oh wait.
Yeah. Well, the notation wise, it just looks so similar. Xi, and then they're going to be utilized in the encoder network.
Yeah, they are going to be utilized in the encoder network, and the encoded result will go together into the processor network, and also the actually we see before that the encoded input is will also go into the decoder network. So the encoded input will be part of the input of the processor network and part of the input of the decoder network.
So if we use multitask learning, then those XIT will also be different for different algorithms.
Yeah.
So we're going to have different branches starting from initial features, I guess.
Yes. Wait, it's starting from which kind of feature are we talking about?
Node features for the graph neural network.
Yeah, but like for the neural network, I suspect that they are using the same. I haven't had time to look at any exact code yet, but I mean, according to their descriptions, I think that it takes in all the encoded input.
If you go to the previous slide, ZT actually is a function of XIT or XT.
Yes. So.
Yeah, so in a multitask learning setting, right? For example, XT should be different for different tasks. But how about this Z and H? Did they mention that experiment?
So at least Z here should be task specific.
I see.
Yeah.
Then H also have to be task specific. So it's like we just go to different branches.
But they claim that like algorithms are executed simultaneously, and also claim that the process network is shared among all algorithms. So according to my understanding is that like H actually takes in all the these from all the different types.
Okay, so HT will be shared.
Yes.
Okay.
And
I have no more questions. Thank you.
Okay. Thank you so much. And yeah, just as like some points that they brings about in the discussing about their algorithms, is that okay? So first they say that the task in this paper only focus on node level representations. Due to that there aren't such many other requirements in the tasks involved in the experiments. But they also claim that this model could easily include some edge level outputs or some graph level inputs and outputs according to different tasks. So it shows the extendability of this model. And also they claim that they didn't consider any of the corner case inputs, like for example, the negative weight cycle or something like this. They didn't consider those corner case inputs. These are part of the works that left to be done in the future. Okay. And pointer graph network, if we are with the prior knowledge that we have from the previous work, the pointer graph network could be regarded as more or less an extension of that work. And the previous works that use a graph neural network to learn the graph algorithms and transfer between them, and using a single neural core to that being capable of doing multiple tasks, not really like handling the core part of multiple tasks. And the pointer graph networks, or PGNs, is a framework that further expands the space of the general purpose algorithm that can be neurally executed this way. Which means that now we are not having a sequence of graphs as the input. We are not specifically targeting at the graph algorithms. Instead, and this problem is extended to the pointer-based structures. And for the pointer, we also have an adjacency matrix. But this matrix is dynamic and could change from time to time, or more or less like the idea of saying that we have the set of vertices and some dynamically changing pi. But previously in the graphs, at least the edges are not changed that much. I mean, the node values are updated through the same set of edges. Okay, here in the PGN, we also have a sequence of inputs as like each representing some sort of operations on the n entities at each step. And EIT is going to be representing the feature of entity I at time t, which is also like we could understand it as denoting some operations like adding or removing edge and etc. And the problem is like predicting the target outputs Y from the given sequence. And some motivation examples will include the disjoint set unions, which is incremental graph connectivity, and also the link cut trees, which is like we could be linking or cutting. So it's fully dynamic tree connectivity. And these are the two major examples getting discussed in the paper. But the structure is pretty similar to before, but yet there's some difference. So previously we have this sort of an examples that in general, we can say that from X and H, we have Z, and from Z and E, we have H, and Z and H have Y. The three components, encoder, processor, decoder, does this. And in the pointer graph networks, we no longer have the how to say, we no longer have the fixed set of edges, but we have previous stage pointers, and we also have some E representing the operations on each step. And if we write it out, it looks almost identical to the previous version that we are having here. And also, like, we are in the decoder network, there also involves some sort of aggregator. And the encoder and the decoder networks are also implemented as simple as just linear projections. The processor network also uses message passing neural networks. And also, there's an inductive bias by nature that, like, most of those algorithms, the known algorithms existing these days, they only modify a small subset of the entities at each step. So knowing this, they also want to mimic this this sparsity. And they achieve it by introducing a mask called a mu-i for each node at each step. And mu-it is said to be 1 if an output of a wait, sorry, just I'm thinking of, like, probably I wrote the wrong thing here. It shouldn't be ZIT and ZIT. Sorry, in the paper. Oh yes, sorry. The second ZIT should be HIT. So this is the masking is computed through a masking network that's takes in the encoded input and the hidden state into consideration, and implemented as a linear layer with a proper dimensionality. And the output activation is the logistic sigmoid, which forces the probabilistic interpretation. And also, they found in practice that symmetricize the matrix is beneficial, and so the tilde pi is used to demonstrate the pointers before doing the symmetrization, and okay, and so the entities, the entries of this matrix is computed this way by considering the sparsity mask and the previous stage, and also consider the and also consider and also consider whether or not, like, J and I are the closely linked together. And it is interpreted this way because the alpha is a self-attention coefficient computed from H. So so we understand it as, like, if J if J is the one that's like getting the closestly connected to I, then we somewhat name it. We are considered them connected together in the next step. And also, like this time, we also have a similar design for the processor network P component. And with once again, the UM are linear layers with ReLU activation functions, and the aggregator being used is also element-wise maximization, because this one performs the best. Sorry, a lot of typos in the slides. I will correct it later. Sorry for the inconvenience. And visualization of the general process of this model goes like this. So at first, everyone connects to themselves, and also later on, they are getting updated and connect to someone else. And we can see that there's always the sparsity mask mu getting involved in the process and all the other components. And E represents some sort of operations. And this time there are more objectives to train at the same time. So first of all, of course, we have the loss coming from Y prediction, and also they also consider the attention and the ground truth pointers for the next step. And this is computed by cross entropy loss. Well, what does it mean by this is that they want the attention computed according to the hidden states to represent the likelihood of being connected and in the next step. And the output from the mask network, which is the sparsity mask, and we also compare it to the ground truth modification at time t, which means that though being sparse, we already know that who is gonna be updated at the next time step, and so by given this piece of information, we're going to supervise the learning of the masking network as well. And there they claim that the domain knowledge is introduced while training in this way. Some examples as for example, the disjoint set unions, the link cut trees. And those are some examples about what those components look like, maybe help a little bit in understanding. For example, E, we have been keeping on saying that E represents some sort of operations. And so this is how they could be used to represent some sort of operations. And for example, the second component is saying that is node I being operated on, and something like this. And the first component is a priority. That is like when they create the graph, they assign some random priority to each node for the same reason why they are assigning the different assigning like different weights to the edges in the previous work. And some of the informations are stored in the pointer adjacency matrix. And we have the ground truth pointer adjacency matrix in the masked. node and the node mask information, and those are the with a hat on it. Those are the ground truths at supervision signals that we are going to provide to the graph. Yeah, and the results. I didn't include those tables in, but basically it shows that their results outperforms most of the existing works, and including like deep sets, something like that. They didn't compare to too many baselines, only deep sets and maybe GAT. And so there are many other related works, and I guess that like so far I can't say that I am exploring every corner of this work well, but I have tried my best, and I still recognize that there are a lot more related work left there to be explored, like the deep sets, and also some other related works like the neural programmer interpreters. That one is also somewhat related to this. And they also, like in the author's talk, he also mentioned an application to reinforcement learning. This is what his comment on this piece of work. And this is called an XLWIN, and this one is in the NERP's workshop. Those are some additional works to be said, and that's all for today's discussion. I can't hear anyone. Is there anyone speaking? No.
Thank you.
Thank you, Patricia. Yeah, I think the neural execution idea is very intriguing. Thank you.
Yeah, thank you. And